Hello all, good evening. Welcome back to my YouTube channel all about VLSI. Hope you're all doing good. Yeah, I hope my voice is audible and my screen is also visible. So let's start today's session. Today we are going to start with a topic called Karnaugh maps or K maps. Okay. Yeah. So let us start today's session. So before starting today's session, please make sure that you have subscribed to our YouTube channel all about VLSI, right? Yeah. So let us see what is meant by K-maps or Karnaugh maps. So basically these Karnaugh maps or K-maps are visual tools used to simplify Boolean expressions. Okay, the Boolean expressions we have seen, right? So for simplifying those Boolean expressions, we use these visual maps or K-maps for simplifying our Boolean expressions easily and make it easier to design and optimize our digital circuits. So basically to solve the complex digital Boolean expressions, we use these K maps. Okay, so with the help of these K maps, actually we can solve our Boolean expressions easily. For examples, if we have a Boolean expression, let's say a b bar c d bar plus a b c d plus a bar b c d bar plus a bar b bar c d plus a b c d whole bar. Okay, so like this, if we have some Boolean expressions, not a b c d whole bar, let's say a b c c bar d. Okay, so like this, if we have any Boolean expression, what you can do, we can take the terms common. What we will do, basically we will take the terms common and we will do some simplification and we apply De Morgan's law or something, and we try to simplify this particular Boolean expression. Okay, manually we will through the steps we will follow some particular steps and we will solve this particular Boolean expression, right? But instead of solving this time taking Boolean expression step by step, what we can do, we can use our K maps or Karnaugh maps. So it is basically a technique for solving our Boolean expressions, Okay, so that techniques we are going to see how to implement this K maps to solve our Boolean expressions. Okay, so why K maps are used? So they are basically used in they are basically they are used in reducing the complex Boolean equations by grouping terms to create minimal representations, ultimately saving time and resources in digital circuit design. Okay, so this Boolean equations can be solved using the K maps so that we can decrease the time taken for solving this particular Boolean expressions. So with the help of the K maps, we can actually solve this. Boolean expressions in a very less time. Now, so basically, this K-map is used to find input variable redundancies also. So, and to reduce the output Boolean equation, let's say suppose if we have a plus ab, okay. So to solve this equation, we will take a common, a into a into 1 plus b. Okay, that is nothing but 1 plus b is nothing but 1, so we will have a. Okay, a, if we take common, a into 1 plus b. Okay, b plus 1 is 1, so finally we are left with a. So here ab is a redundant term. Here ab is a redundant term. You can say it is a redundant term. It is not used. It is not it will get cancelled out if we solve this particular Boolean expression. So this type of redundant terms can also be solved using the K maps easily. Okay, without solving these equations, we can easily solve this redundant terms easily with the help of the K maps. Okay, so that is how we are going to use this K maps for solving the redundant terms also. So basically, K map is a chart or a graph composed of an arrangements of adjacent cells. So basically, K map will have a adjacent cells. So like this, a K map will look like this. So it is a chart which consists of adjacent cells like this. Okay, composed of arrangement of adjacent cells, each representing a min term or a max term. So this K map, each cell can represent a min term, it can represent a min term, or it can also represent a max term. Okay, depending upon the equation which is given to us, whether it is a POS form of representation or a SOP form of representation. About the POS and SOP form of representations we have already discussed in our previous sessions. If you haven't watched that, please go back and revisit those concepts. Okay, so whether the given equation is a POS form of representation or a SOP form of representation, okay, depending on the type of representations, each cell will represent whether it is a min term or whether it is a max term. Okay, each cell will represent whether it is a or whether it is a max term. Okay, depending upon the type of equation, whether it is a SOP or POS. Okay, now, so like a truth table, it means showing the relationship between the logic inputs and desired output. So the K map also shows the relationship between the logic output and logic input. And the number of cells, so how many number of cells should a K map have, that will depend upon the number of variables. Okay, I will write it here. So the number of cells in a K map, the number of cells in a K map will depend upon the number of, in the Boolean expression, number of variables in the Boolean expression or in the Boolean function. Okay, how many number of cells that K map should have, that will depend upon the number of number of variables in that particular Boolean function. For example, if it is a Boolean function of 3 variables, f of a, b, c, then the number of cells will be equal to 2 power 3, which is equal to 8. Okay, this is equal to power of number of variables in the Boolean function. So if there are 3 variables, then the number of cells the K map consisting is equal to 2 power 3, which is nothing but, which is equal to 8. 2 power 3, which is nothing but, it is equal to 8. If you are having two number of variables, that is f of a comma b, then the number of cells in that particular K map will be equal to 2 square, which is equal to 4 number of cells. So for two variable Boolean function, the number of cells in the K map is equal to 4, and the 3 variable Boolean function, the number of cells will be equal to 8. Similarly, for 4 variable function, the number of cells will be equal to 2 power 4, which is equal to 16, and 5 variable function, the number of cells will be equal to 2 power 5, which is equal to 32. Okay, and the number of cells, so if the number of cells are equal to 3, or it is equal to 4, 3 is not possible. If it is equal to 4, then it is called 4 variable K map. Then it is called as 4 variable K map. Or if it is equal to, 2 variable K map. And if it is equal to, a number of cells is equal to 8, then it is called as 3 variable K map. 3 variable K map. Okay. And the K map will be up to 5 variables only. 5 variables only. That is 32 cells. That is 32 cells. So the number of highest cells, 32 cells, we can go up to 2 power 6 also, but it will be difficult. There will be difficulty in solving this particular K map. So we will be stopping our discussion up to 5 variable K map. That is 32 number of cells. Okay, I hope this is clear now. So a n variable will have 2 power n possible combinations and 2 power n number of cells. So it is both applicable to SOP form of representation. Okay, yeah. So this is how we are going to form a K map. Now let's see the different types of K maps which are present. Okay, so here which is written, K map is a grid-like diagrams where each cells represent a unique combination of variables states in the Boolean function. The number of cells in the K map depends upon the variables. So for a 2 variable K map, the number of cells will be equal to 4 cells, and a 3 variable K map, the number of cells will be equal to 8 number of cells. Okay, and for 4 variable, the number of cells will be equal to 16 cells, and each cell corresponding to the min term or a max term. Okay, and each cell is corresponding to a min term or max term. Okay, now let's see different type of K maps which are present and the structure of K maps. Okay, so let's see a 2 variable K map first. 2 variable K-map. Let us see a2 variable K-map first. Okay. So this is a if it is a function of f of a comma present in a Boolean function f of a comma b, then how to represent a two variable K-map? So this is how we are going to represent a two variable K-map. And it consists of how many cells? 4 cells. Since two variables, then number of cells will be equal to 2 power 2, which is equal to 4 cells. It is equal to 4 cells. Now, so we will write the variables here a, b, or you can write b and a. Okay, no issue. A, b. Now, here I will represent 0, 1 and 0, 1. The possibilities of a and b. A can be 0, A can be 1, and B can be 0, B can be 1. Okay. Now, this is my SOP form of representation. Okay. This is my SOP form of representation. So, in the SOP form of representation, for 0, if A is equal to 0, then it is represented as A complement, and if B is equal to 0, it is represented as B complement. And if A is equal to 0, this particular row or this particular column is corresponding to A, and this particular row is corresponding to B. Okay, so in this particular column, if A is equal to 0, it is represented as A bar, and here B is equal to 0, so it is represented as B bar. Now here, if A here in this column A is 0 only, so it is equal to A bar, and here B is 1, so it is represented as its normal form. Okay, so in SOP form of representation we have already seen. So to represent 0, we represent that particular variable with its complement form, and for 1 it represents it in normal form, that we have already discussed. Now here, if here in this column A is equal to 1, so it is represented as A, and B is 0, so it is represented as B bar. Okay, and here A, B. So A bar B, AB bar, AB. So this is how you are going to represent a SOP form of representation, and this is min terms. So each cell in this K-map are representing min terms. Each cell in this K-map are representing min terms. If you observe carefully, these are nothing but the min terms. If you see the truth table, these are my inputs A and B, and this is my output Y. Okay, so what are the min terms? 0, 0. What are the possible combinations? 0, 0, 0, 1, 1, 0, 1, 1. That is A bar, B bar. Output may be anything. Okay, A bar, B, A, B bar, A, B. So these are all the min terms. So each cell in this particular K-map is representing a min term. Okay, so this is how you are going to represent a SOP, a two variable K-map for a Boolean function, which is in the form of SOP. Now we will see for POS form of representation, the K-map for POS. Okay, same two variable function f of a comma b. Okay, now how to represent this? Same, the diagram will look same. Okay, here A and here B. So 0, 1, 0, 1. Okay, now so this cell number also, here it is 0, this is 1, this is 2, this is 3. This is cell number 0, or the min term value, it is 0. Here the min term value is 1. Here the min term value is 2, 3. Okay, here the min term value will be equal to 0, 1, 2, 3. Here I am representing the min term values. At the top of the cell, at the top of every cell, I will write the values of the min term. Sorry, if it is a min term, I will write the values of that min term. And here in this case, I am writing the values of the max terms. Okay, so here each cell represent a particular corresponding max term. Each cell represent a corresponding max term. So in this case, what is a max term? Which is nothing but A plus B. Okay, here A is in POS form of representation, 0 is represented as normal form A. Okay, the variable is represented as its normal form, and B is also normal form. And here in this particular column, A is equal to 0, it is represented as normal form, and here B is 1, so it is represented as its complemented form. And here A plus B bar and A bar plus B bar. If you see the POS form of representation of 0 is A plus B, and for 1 is A plus B bar, and 2 is A plus B bar, and sorry, for 2 is A bar plus B, A bar plus B, and for 3 is A bar plus B bar. So this is how you are going to represent your max terms in a two variable K-map. Now, how to represent a three variable K-map? So for a three variable K-map, let us take the example of first min term and then we will go to the max terms. Okay. So for let's see the min terms for this three variable K-map. Let's say if you have a function of f of a comma b comma c, so 2 power 3, which will be equal to 8 number of cells. Okay. So how many number of cells are possible for this three variable? So total 8 number of cells are possible for this three variables. How to draw the K-map for this three variable? So this is how we are going to draw three variable K-map. 1, 2, 3. Okay. A, B, C. Okay. B bar, C bar, or you can write this representation. I will show you in later slides. For now, we will follow the first representation. I'll draw it again. This is a 8 variable K-map and we have A, B, C. Okay. 0, 0, 0, 1, 1, 1, 1, 0. Here the value of BC can be 0, 0, 0, 1, 1, 1, 1, 0. And the value of A can be 0 and 1. If you observe, here I am using 1, 1, not 1, 0. Why? Here 0, 0, 0, 1, 1, 1, 1, 0. If you observe the definition of K-map, what we have seen, the K-map will consist of adjacent cells. The K-map consists of adjacent cells. What is meant by adjacent? Adjacent is nothing but next after. Suppose if what is the adjacent number of 1, it is equal to 2. What is the adjacent number of 3, which is equal to 4. This is the adjacent numbers. But in binary, if you observe, so here what you are observing, there is only one number change. 1 is 1, 2. Okay, there is only one number change. 3 is 4. Not you cannot. Okay, 0, 0, 1 and 0, 1, 0 are adjacent numbers. And but if you observe 0, 1, 0 and 0, 1, 1, there are 2-bit changes. There is change in 2 bits. Here 0 is changing to 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Not here. There is 1-bit change only. There is 1-bit change. Sorry. And here in the next step, if you observe, 1 is changing to 0 and 1 is changing to 0 and 0 is changing to 1. So if you observe, there are 3 bits changes. There are 3-bit change. So that's why. And if you observe the two variable 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 0 to 0, 1. There is only 1-bit change. There is only 1-bit change. So you can see these two are adjacent numbers. And from 0, 1 to 1, 0, 0, 1 to 1, 0, if you observe, 1 is changing to 0 and 0 is changing to 1. So there are 2-bit changes. There are 2-bit changes. And so you cannot say these two are adjacent. These two are adjacent. No, these two are not adjacent. You cannot say these two are adjacent. But 0, 1 and 1, 1 if you compare, 0, 1 and 1, 1 if you compare, 1 is constant, only 1 bit is changing. So this is adjacent. So it is adjacent. So that's why we are going to use this type of nomenclature 0, 0, 0, 1, 1, 1, 1, 0. So 1, 1 is adjacent to 0, 1. Okay, that's why we are going to use this number representation. So we are going to represent only the adjacent numbers of the particular cells. Okay, so what is the value of this particular cell? 0, 1, 1, 1 means 3, and this is 2. This is 4, 5, 7, 6. 0, 1, 3, 2, 4, 5, 7, 6. Okay, so these are the adjacents. Now, so what is the value of this particular min term, which is nothing but A bar, B bar, C bar, A bar, B bar, C, A bar B C, A bar B C bar, okay, A B bar C bar, and A B bar C, A B C, and A B C bar. So this is how you are going to write the particular minterms for every cell. Now, coming to POS form of representation also, max terms also, if you observe, the structure looks the same and the numbering is also same, but we will use max terms. That's it. A, B, C, B bar, C bar, B bar C, B C, B C bar, A bar, A. Okay. 0, 1, 3, 2, 4, 5, 7 and 6. Not 6 and 7, 7 and 6. So here it is equal to A plus B plus C. Why 0 is represented as A plus B plus C. 3 variable key map. For the max term, we are writing for max term. Okay. And next one is nothing but A plus B plus C bar. A plus B plus C bar. And next one is A plus B bar plus C bar. And next is A plus B bar plus C. And followed by A bar plus B plus C. And A bar plus B plus C bar. A bar plus B bar plus C bar. A bar plus B bar plus C. So this is how you are going to represent a max term, K-map for a max terms. Okay. Now let us see how to represent a 4 variable K-map. So for a 4 variable K-map, let us say there are 4 variables A, B, C, D. That is 2 power 4, which will be equal to 16 cells. 2 power 4, which is equal to 16 cells. So let us draw our 16 cells. Okay. So let's say A, B, C, D. What are the possible combination of CD? 0, 0, 0, 1, 1, 0, 1, 1. Here 0, 0, 0, 1, 1, 0, 1, 1. So these are all the possible combinations of ABCD. Okay. Now ABCD can be represented. This is for minterms. How to represent the minterms? A bar, B bar, C bar, D bar, A bar, B bar, C bar, D. So like this, you can fill up all the minterms. And here if you observe, it is not 1, 0, 1, 1. It is 1, 1, 1, 0. It is 1, 1, 1, 0. And here also it is 1, 1, 1, 0. Okay. So like this, you can fill up all the minterms and finally you can fill it up to A, B bar, C, D bar. Okay. Which is nothing but 0, 1, 3, 2, 4, 5, 7, 6. And here 8, 9 will not happen because this will be not adjacent to this 4, 5, 6, 7. Okay. Here 8, 9, 11, 10 and 12, 13, 15, 14. You can apply the same explanation which we have discussed in our previous slide, right? This explanation, why you can apply this explanation to this particular concept, why we are writing 8, 9, 11, 10 to this particular and 12, 13, 15, 14 here. Okay. So this is about 4 variable K-map. And your homework is to write the 4 variable K-map for max terms. Okay. This is one type of representation. And another type of representation what we can use is for 2 variable SOP form of representation. What we can do, SOP 2 variable, I'll write it here. A, B, you can write B bar, B, A bar, A. This is one type of representation. Instead of writing 0, 1, 0, 1, you can write A, B bar B, A bar A. So this is, I feel this particular implementation structure is somewhat easy. And you can also interchange. You can also write like this also. B, A bar, A, B bar, A. You can also interchange. And for 3 variable, how can you write? 2, 3. A, B, C. B bar, C bar, B bar C, B C, B C bar, A bar A. Or you can also interchange. You can write here B and you can write here AC. A bar C bar, A bar C, AC, AC bar, B bar and B. So this is also, this way also you can interchange and you can represent your K map. This is one more form of representation. Okay. So this is how you are going to draw a K map, and you can represent a K map for all the variables. Okay. Next, let us see how to group variables of a K map. Okay. So for grouping of variables, there are basically several type of groupings. Let's see one by one. So grouping of two adjacent cell pairs. Two adjacent cell pairs. So grouping of adjacent cell pairs. Two adjacent cell pairs. For example, if we have a K map, 4 variable K map, okay, let's say this is our 4 variable K map with A, B, C, D present here, C bar, D bar, C bar, D, C, D, C, D bar, and A bar, B bar, A bar, B, A, B, and A, B bar. 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15, 14. So let's say this is our 4 variable K map. Okay. Now, if we have minterms, let's say here, here, let's say here. So how to group minterms? Let's see grouping of adjacent minterm or cell pairs. So these two cells are adjacent to each other, so you can group them. Okay, these two cells are adjacent to each other and you can group them. But these two cells are not adjacent to each other. Crosswise, these two cells are not adjacent to each other. Okay, so only the linear wise, only the same horizontal wise, the cells are adjacent. The cells will be adjacent. So no cross grouping is possible. Okay, no cross grouping should be done. Only the linear grouping should be done. So for example, if we have a minterm here, we can group this 2 terms and we can group this 2 terms. Okay, and the corner cells can also be grouped. So these 2 cells, these 2 corner cells can also be grouped. This is also possible. Okay, let's see for a 2 variable K map, the grouping for a 2 variable K map. What are all the possible groupings are possible? So this is our, let's say this is our 2 variable K map, B bar, B, A bar, A, 0, 1, 2, 3. Okay, now, so let's say here we have our minterms. Okay, you cannot group them crosswise. In a cross fashion, you cannot group them. Okay, but what if we have a minterm here, you can group these 2 minterms. This grouping is possible, and you can also group these 2 minterms. Okay, and you can also group this like this also, adjacent corner cells. And okay, so this is about grouping of 2 adjacent cells. Here we are grouping only 2 adjacent cells. Okay, and let's see grouping of 4 adjacent cells. I'll write it here. Grouping of 4 adjacent cells. So what we have seen previously, we have seen grouping of 2 adjacent cells. Now let's see the grouping of 4 adjacent cells for a 2 variable K map. We will start with the 2 variable K map only initially. B bar B, A bar A, 0, 1, 2, 3. Okay, 1, 1, 1, 1. If we have minterms like this, so these 4 minterms can be grouped. Okay, so this is nothing but grouping of 4 adjacent cells. So this is how we can group a 4 adjacent cells and 2 adjacent cells in a minterm. So in a K map. Okay. So that's all for this session. So in next session, we will see how to group 4 adjacent cells, 8 adjacent cells. Okay, grouping of 4 adjacent cells, grouping of 8 adjacent cells, that will come that in 8 variable K-map and 16 variable K-map. We will see all that. Okay. Yeah. So that's all for this session. So if you like this session, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.